Hello, I'm pleased to participate in the Mission Critical Water Virtual Conference, and I appreciate your participation as well. Meeting the water challenges facing the planet will require input from all of us, in business and industry, in science and research, in NGOs, in governments, and in the fields and farms where some 70% of the world's fresh water is used. Only through partnerships and collaboration will we develop solutions that enhance water sustainability while meeting the essential goal of agriculture, growing the food that feeds the world. Today I'll examine agriculture-based solutions to the global water challenge. I'll also discuss why we should approach water challenges holistically, incorporating all the tools and technologies available to increase water efficiency in agriculture as well as in other areas. At Syngenta, we bring plant potential to life. But plants and environments vary, which means that realizing plant potential requires a variety of solutions. Think about it this way. If we go to the Olympics, we'll see many athletes who run fast. But not all runners specialize in the same competition. Maximizing performance in a marathon requires different qualities than winning the 100 meters. And similarly, different qualities and skills differentiate success in sprints and hurdles. The same concept applies to plants, environments, and methods used to achieve best performance in the field, where water is a key driver of performance. Obviously, water and agriculture are linked, or as some may say, tied at the hip. When thinking about the water needs of agriculture and applicable solutions, Syngenta focuses on three major water-related risks that a farmer may face. The first is availability risk. Is water available in the right quantity, of the right quality, and at the right time? For instance, in Australia or Israel, lack of water is the problem. In India, on the other hand, the issue in many cases is both quantity and quality, as farmers often irrigate using saline or salty water, which is pumped from deeper and deeper within underground aquifers that are depleted faster than they can be naturally replenished. Second risk is climatic, a once-in-a-while climatic event like a drought in Russia or a flood in Pakistan. Whereas availability risk is an ongoing, constant issue, climatic events are more sporadic, requiring risk management or insurance because they may occur, say, this year and not reoccur again until several years later. Of course, the longer-term risk of climate change may make serious climatic events more frequent and thus requiring additional thought on how farming practices and technologies should evolve to cope with new stresses. The third risk we focus on is economic. This could relate to the cost of the water itself, the cost of the energy to pump it, and the cost of inputs used on the farm, and of course the yield output and the price the farmer receives for his produce. In other words, all the various factors impacting the farmer's profit and loss. This then raises the question, which solutions can be brought to bear to mitigate or control each of these different types of risk? How can we ensure that a grower gets optimal productivity with the water and resources they have today or will have tomorrow? How can we enable farmers to use these resources sustainably? So now let's look at some solutions. One example we have been working on at Syngenta is our water-optimized corn hybrids, which will come on the market this year. These hybrids are called water-optimized because they have demonstrated increased drought tolerance and can thus be grown in suboptimal conditions. This, of course, will help address climatic risk and water availability problems. At the same time, some of these hybrids use water more efficiently and thus need less water on an ongoing basis. This capability can help address the irrigation and pumping costs in many parts of the world, such as the dry plains of Nebraska in the United States, to give just one example. Nebraska, and indeed many of the top grain-producing states of the American Midwest, draw irrigation water from the vast underground reservoir known as the Ogallala Aquifer. Unfortunately, that aquifer is being drawn down faster than it can be replenished. And the depletion of aquifers is, of course, a critical challenge in many parts of the world. Mexico's aquifers are being drawn down 20% faster than they can be renewed by rainfall. In China, aquifers are being depleted at a rate of 25%. As fresh water is drawn out of India's aquifers, they become increasingly salty. At some point, they may no longer be usable. Decreasing the amount of water needed by crops is therefore a critical component in strategies to preserve this critical resource. Optimizing the available water and land is another. If you look at this picture of pivot irrigated fields, you'll see another potential application of water-optimized crops. Of course, we can improve the productivity and efficiency in the irrigated area. However, the spaces at the corners of these circles get little water and are therefore underutilized. Enabling crops to grow in these non-irrigated corners of the field could help maximize the farmer's yield and optimize the usage of his land, all without any added irrigation water. Low-yielding and drought-prone rain-fed areas would benefit from similar approaches. Other examples of solutions to agricultural water challenges include chemistries known as crop enhancement products, which change the physiology of the plant. One effect of such chemistries is reduced transpiration and increased efficiencies so that the plant loses less water through their leaves. Another is deeper and larger root systems that allow the plants to access water deeper below the Earth's surface. Thirdly, the use of pesticides prevents crops from being lost due to pest or disease. Not using them would represent a pure loss of the water that went into growing those plants. And finally, just as critical are herbicides to control weeds to prevent crop loss. Weeds compete with the crop for both water and soil nutrients. The more weeds, the more competition for water, and thus waste. Speaking of waste, a huge percentage of water used to irrigate crops is simply wasted. The average around the world is about 40% that is wasted because it's not used by the plants and considered lost. This usually occurs because of inefficient irrigation practices, which lead to water not being used properly and ends up evaporating or running off. There is no doubt that irrigation practices need to improve, as most farmers do over-irrigate. But this is not a surprising fact. Water is the most important factor in plant survival and crop yield. Overwatering is therefore a perceived means of insurance so that the plant will not suffer a loss. Overwatering is not actually needed and may even harm the plant, but if a temporary water stress arises, farmers worry that it will be almost impossible to recover from it. Now, who wouldn't naturally prefer to be rather safe than sorry? In order to address this perception and produce the desired savings and efficiencies, as well as improved yields, growers need better ways to manage inputs and the growing of the crops themselves. These include the plant tools and technologies I just described, but there's also an additional layer of technologies which helps monitoring field conditions, both proactively and in reaction to specific events. Examples of technologies that improve farm efficiency include better weather prediction, on-site weather stations, soil moisture probes, as well as new technologies that measure vigor, greening, photosynthesis, and many more. You see a few examples of such devices pictured here. These help the grower, much like in any manufacturing or production system, to manage the operation of the field, understand what is driving production, and preempt problems. In a sense, they are quality control devices all along the production chain that allow constant monitoring and adjustment. The difference is that a factory floor is a controlled environment. The farm field is more at the mercy of the elements, or at least has been up to now. In other manufacturing or production systems, success in improving productivity and efficiency required the entire system to work together, not just one isolated component working individually. For instance, using the most accurate soil moisture sensor would tell you that the moisture is at a certain level, but the grower still needs to combine that data with all the other field data. This would include weather forecasts, soil type, analysis, and perhaps more importantly, the specific plant's genetics, physiology, and chemistries which were applied, which altogether enable different management of water and other environmental conditions and risks. because each field and farm is different, such understanding will allow farmers to customize and tailor water use and growing practices. To give an example, say a corn grower in Nebraska measures X amount of moisture in the soil. That measure could indicate insufficient water on his farm, requiring an additional 1 inch of irrigation water per acre. On another farm or in another field within his farm, that existing moisture might be sufficient or require only ½ an inch of additional irrigation water per acre. How much water would that save? Using ½ an inch rather than 1 inch per acre is savings of 50%. That's approximately 50,000 liters per acre in that one irrigation cycle. Now, according to the USDA, the average farm size in Nebraska is close to 1,000 acres, and that would mean 50 million liters of water in an average Nebraska farm. There are significant scientific challenges to creating this type of algorithm with so many variables and changing conditions. Not only is agriculture very local, but inputs such as water vary widely between geographies in quantity and quality, as well as source, flow, and much more. To solve this riddle, we will need to bring together the best in genetics, agronomy, and chemistry, as well as the best in data mining, forecasting, digital technology, weather, local and remote sensing, agricultural machinery such as tractors, planters, combines, and so on, as well as irrigation systems. All of these data and inputs have to be integrated into decision-making tools that work on the farm and at the aggregate level. Syngenta is already working with multiple partners to address these challenges. Our solutions embrace everything from irrigation to soil management to sensing and other components, all tailored to local solutions for growers based on crop, region, climate, soil, and many other parameters. And all are brought together to achieve optimal and sustainable production with more automation. This is no easy task. If we were to compare these efforts to scientific advances and efforts in human health, we would not be aiming at just solving a single disease or stress. Actually, we would be adapting human genetics, nutrition, habits, and living conditions for optimal performances suited to each of many different environments, from Africa to Siberia, and from Beijing to Wall Street. Because the effort is so complex, it cannot be accomplished by any one particular company or even by the public or private sector alone. Syngenta is actively looking for alliances and partnerships with various companies ranging from well-established multinationals to startups. We're also looking for partners in academia, NGOs, and the public sector who bring unique tools and perspectives to ensure that the planet's available water and other resources can help sustain us in the decades to come. So far, I've focused on agriculture, but our view of water and the issues around it is more holistic, from water source to the farm and moving all the way through the entire value chain. Water is a key part of almost everything that happens in this world, from basic human needs such as hydration, food, and sanitation to almost every kind of industry. Water is key to the environment. The water cycle of evaporation, condensation, and precipitation is what gives life to our planet across regions and climates. We believe that solutions must therefore address and incorporate the full spectrum of water challenges. As this chart highlights, 70% of the fresh water we use goes to agriculture. Yet the 30%, which is for domestic and industrial use, is actually where most of the attention is focused, and hence, most of the investments in innovation. Water technology companies tend to focus on developing technologies for wastewater treatment, desalination, hydroelectric dams, water harvesting, and more. These investments are critical and needed, but the current trends for food, feed, and energy make it clear that the needs of agriculture will continue to be significantly higher than those of domestic and industrial uses due to the water-intensive nature of growing crops. Agricultural solutions to the water challenge are mostly focused on demand efficiencies, while industry is mostly focused on increasing supply, demand, supply, The solution as a whole is a combination of the two. Water and resources can be used and reused across industries. An example of such relationships already exists today, but they are not optimized nor leveraged for impact. So imagine a wastewater treatment plant in a municipality with nearby agriculture, perhaps in China. Simplified, the input for the wastewater treatment plant is, not surprisingly, wastewater, and the outputs are two: clean water and the waste, also known as sludge, which is then solidified. Now, companies operating the treatment plant burn the sludge, or in many cases, just give it away to farmers to spread on their fields as fertilizer. It contains nutrients which are not necessarily the choice of humans, but are actually very welcomed by plants. This process is a good start on collaboration between agricultural, domestic, and industrial uses of water. But we can go even further by making the process more efficient and tailoring the outputs to help maximize water efficiency and crop production based on local and regional conditions. Similarly, discussions of water infrastructure and subsidies should also include irrigation systems and incorporate all agricultural inputs, such as seeds, crop protection and crop enhancement chemistries, fertilizer, and machinery, to focus on securing food rather than just water supply. Consider India, where the government already provides subsidies for drip irrigation so that farmers become more efficient. This is already a significant achievement. However, the purpose of agriculture is food production, not just water supply. As such, it makes sense to align irrigation incentives with water infrastructure, quality, and the crop itself, asking which is the best crop to grow and how can it best be grown in that particular region under the prevailing conditions. These are just a few examples, and I'm sure we can build many more such linkages and foster better discussion to find more integrated solutions. We should avoid further discussion and debate on solutions that are fragmented or compartmented by industry. I hope I've provided you with some food and water for thought. I look forward to hearing additional thoughts about these and other solutions in the coming sessions. The challenge is a huge one, but solutions are possible if we think about water more holistically and if we collaborate, taking into account all options, how to improve efficiency, and how to work together to make these improvements a reality. If we do that, I have no doubt that we can continue to grow more from less, feed a hungry world, and ensure a sustainable water future for ourselves and future generations. Thank you.